glucogenic acids, then lactate, then glycerol. Where do we get glycerol? Ah, okay, breakdown of triacyl glycerol. All right. And propionate or propionic acid. Now, the fatty acids that we have is even number 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, even numbered. However, ruminants, ruminants, those eating grass. So animals eating grass. Okay. Have fatty acids which are odd numbered. So odd numbered. 3, 5, 7, 9, and so on. Odd numbered. Now in the metabolism of fatty acids, 2 carbons are removed at a time. 2 carbons are removed at a time. And those 2 carbons are in acetyl-CoA. Now, if ever you what you call fatty acids with odd numbers coming from the food that you eat, coming from ruminants, cows, carabaos, goats, sheep, no? The last 3 carbons of an odd numbered fatty acid is propionic acid. So that is the source, propionic acid, propionate. No? So again, our sources are glucoamino acid. We have, if you still remember our amino acids, we have glucogenic, ketogenic, and both glucogenic and ketogenic amino acids. We have categorized our amino acids. Okay. So glucogenic amino acids, lactic acid, and propionic acid. And liver and kidney are the major glucogenic tissues. The kidney contribute about 40% of the total glucose synthesis in the fasting state and more in starvation. So these 2 important organs, the kidneys and the liver. Okay. The gluconeogenic enzymes or the enzymes for gluconeogenesis are also expressed are also expressed in the small intestine. But it is not clear whether there is a significant action of glucose in the system. As we said earlier, our principal organs for gluconeogenesis is your liver and kidneys. Huh? All right. Let's continue. We know already that organs that require glucose, the nervous tissue, and the erythrocytes, or the red blood cells. Now, however, in extreme fasting, the nervous system will shift to another use of fuel, and that it can use ketone bodies. Now, that shifting signifies that there is a dire need of glucose. And whatever glucose is left is for your red blood cell, because your red blood cell cannot utilize any other fuel except glucose. And it says here that failure of gluconeogenesis is usually fatal. Even low glucose brings about brain dysfunction, which can even lead to coma or death. Glucose is also important in maintaining adequate concentration of intermediates of the citric acid cycle. And you know how important is the citric acid cycle in the tissue. And also, gluconeogenesis is very, very important in removing lactic acid produced by muscles in anaerobic glycolysis and in erythrocytes. Because erythrocytes, or your red blood cell, the manner by which they form energy is through anaerobic glycolysis. I point this out, no, this one earlier in our lectures, that although your red blood cell carries oxygen by way of the hemoglobin, it cannot use that oxygen. For the simple matter that your red blood cell does not contain a mitochondrion. And it is the mitochondrion which has the electron transport chain which utilizes oxygen. So, in a cell where there is no electron transport chain, they cannot utilize the oxygen. So it is really paradoxical on the part of your RBC. They carry oxygen and yet they cannot use it. It is just like when you are in lifeboat because of a typhoon, you have not landed any shore, you're still in the sea. There's plenty of water around you, and yet you cannot drink it. Diba? No, that's the same as with your RBC. Plenty of oxygen, but it cannot use it. Right? So we have there, I mentioned this already. Glycerol produced by adipose tissue. Romance propionate is a product of bromine metabolism of carbohydrates as a major substrate for gluconeogenesis. Okay. There is excessive gluconeogenesis that occurs in clinically ill patients in response to injury and infection, contributing to a high amount of glucose in the blood, which usually is associated with a very poor prognosis because it leads to hyperglycemia. And if there's so much of glucose in the blood, the osmolality of the body fluids changes, and it impairs blood flow, producing intracellular acidosis and increased formation of superoxide radicals. And then your immune system will be overwhelmed and impaired blood coagulation. Excessive gluconeogenesis is also a factor to increase of glucose in type 2 diabetes because of impaired down regulation in response to insulin. Now you should remember, in type 2 diabetes, it does not mean that the patient does not have insulin. It has insulin. The problem there is the receptors for insulin. You know, insulin is water soluble, and it cannot just go directly into the cell without receptors. And if the receptors are not there, then your tissues are insulin insensitive to insulin. Okay? So, glucogenesis is synthesis of glucose from compounds that are not carbohydrate. Oh, that is, we mentioned that already. In humans, our major precursors of gluconeogenesis are lactate, glucogenic amino acids, glycerol, propionic acid. The fatty acids, the one that we mentioned here, fatty acids, are the even numbered. The fatty acids that we produce. So, the fatty acids that we have cannot produce any net glucose, except if we eat fatty acids which are odd numbered fatty acids. And the remaining 3 carbons of the fatty acid in the fatty acid metabolism through beta oxidation is the one that is converted to propionic acid. Gluconeogenesis is not a reversal of glycolysis. It requires, because in your glycolysis, there are 3 areas where the process is irreversible. It is irreversible. And so, we need to have other reactions in order to reverse it. Reverse the flow. Now, reversing the flow of your glycolysis by intervening in these 3 irreversible steps of glycolysis. We will show it. Okay. We continue. Glucogenesis involves glycolysis citric acid cycle, and some special reactions. These special reactions occur in the irreversible steps of glycolysis. It says here, thermodynamic barriers prevent a simple reversal of glycolysis. Three, non-equilibrium, or meaning irreversible reaction in glycolysis, catalyzed by hexokinase. That's the first one. Hexokinase or glucokinase, if it is in the liver, then phosphofructokinase and pyruvate kinase prevents simple reversal of glycolysis for glucose synthesis. They are circumvented by special enzymes. Here we are. Can you see this? Is this clear? Hello?
Yes po, Doc.
You can see this. All right. Starting from glucose, this is phosphorylated either by glucokinase or hexokinase and becomes glucose 6-phosphate. This is found in your book. Okay? That is irreversible first reaction. The second irreversible step is phosphofructokinase. There. And the third step is this one, pyruvate kinase. Look at the arrow. This is irreversible. This is also irreversible. This is irreversible. You see that? Oh, this is your glycolysis. So we need to bypass this. You need to bypass this. What did it say? Gluconeogenesis employs the glycolytic enzymes, the citric acid cycle enzymes, and special enzymes. And what are these special enzymes? Starting from here, we have this glucose 6-phosphatase. No? This one, fructose 1,6-biphosphatase. And this one is bypassed by this carboxykinase. Now, you will know that these bypass enzymes are because you notice that it has a double, what you call this? Frame. No? Double frame. Double frame. This one is single frame only. Like that, single frame, single frame. Okay? All right. Let's start from let's start from the citric acid cycle. Now this is your mitochondria. Huh? Remember, this is your mitochondria. And this is your citric acid cycle. All right. What do we have here? We have here malate. Oh, an intermediate in your citric acid cycle, which exits out of the mitochondrion into the cytoplasm. You know that. So where does malate come from? Malate come from fumarate, succinyl-CoA, alpha-ketoglutarate. No? Now, the carbon skeletons of your amino acids, the glucogenic amino acids, either they become the carbon ketones that are found in your citric acid cycle. Alpha ketoglutarate is the carbon skeleton of glutamic acid. And your glutamic acid has what we call a glutamic acid family. And try to find out family of that the glutamic acid family. What amino acids are involved in there. For sure, one of them is glutamine, because glutamine is an amide of glutamic acid. All right. Try also to find out what amino acid carbon skeleton goes into succinyl-CoA and to fumarate. All right. Look at this. Pyruvate can become oxaloacetate. Now, if you look at this here, between oxaloacetate and malate, that is reversible. So oxaloacetate can become malate. So your pyruvate can become malate. All right. Now lactate here can become pyruvate. Pyruvate gets inside the mitochondrion, acted upon by this particular enzyme, pyruvate carboxykinase, carboxylase, I'm sorry, carboxylase, and then becomes oxaloacetate, it becomes malate, and once it is malate, it has a transporter and brings this malate out into the cytoplasm. Now, this is oxidized and becomes oxaloacetate. And then it's decarboxylated and becomes phosphoenol pyruvate. Phosphoenol pyruvate, this is a reversible reaction. It can go up, reversible reaction, go up, reversible reaction, go up, reversible reaction, it can go up. Now, this is irreversible. So we employ this enzyme as a bypass enzyme. No? So it bypass that, becomes fructose 6-phosphate. Now, fructose 6-phosphate becomes glucose 6-phosphate by an isomerase. Very easy. Now, that is irreversible. You cannot go that way. So we go this way, we bypass it by using another enzyme. And we form now free glucose. This is a phosphatase, removes the phosphate here, and you have now a free glucose. That free glucose can go out into the plasma, and augments the blood glucose, increases the blood glucose. So there you are. All right. So where is glycerol? Glycerol is here because oxidation, utilization of fatty acids occur in the cytoplasm. And so you have glycerol. And then glycerol becomes glycerol 3-phosphate and becomes dihydroxyacetone. No? And two of that, or one of that and one of this becomes fructose 1,6-phosphate. And so it can go this way, go up, and go this way. So there is glycerol, lactate, propionate, and glucogenic amino acids. Sources, this one is red. You have amino acids there, amino acid, and amino acid. You say now your gluconeogenesis. Okay. So to go back, it's here. Gluconeogenesis in a nutshell. So what is this? First, the precursors. Lactic acid, glucogenic amino acid, glycerol, and propionic acid. Then says is not simple reversal of glycolysis. A number of different enzymatic steps are required. Pyruvate carboxylase converts pyruvate to oxaloacetate in the mitochondrion. No? Just follow that diagram. Oxaloacetate is converted to malate or aspartate, which travels to the cytosol and is converted to oxaloacetate. Phosphoenol carboxykinase, phosphoenol pyruvate carboxykinase, converts oxaloacetate to phosphoenol pyruvate. Then phosphoenol pyruvate forms fructose 1,6-biphosphate by reaching the steps of the glycolysis until you reach fructose 1,6-biphosphate, converts fructose 1,6-biphosphate to fructose 6-phosphate, converted to glucose 6-phosphate. Glucose 6-phosphate converts fructose 1,6-biphosphatase. Okay, this is a phosphatase. Converts glucose 6-phosphate to free glucose, which is released into the blood. A phosphatase. Okay. Then to continue, glucogenesis occurs under condition in which pyruvate dehydrogenase, pyruvate kinase, fructokinase, and glucokinase and hexokinase are relatively inactive. The low activity of these enzymes prevents futin cycles from occurring and ensures that overall pyruvate is converted to glucose. The synthesis of one molecule of glucose from 2 molecules of pyruvate requires 6 molecules of ATP. Okay? So what is the expenditure of energy here? Is 6 molecules of ATP. Okay? That's your gluconeogenesis. There's still so much of this. I think it is too much for you to handle now. So I think we'll just have to stop here, although so many that we'll have to talk about. So we'll just have this tomorrow. No? Okay. Is it okay with you?
Yes, Doc.
Oh.
Yes, Doctor.
Thank you, Doc.
Thank you, Doc.
Oh, we'll continue tomorrow.
Yes.
Okay. Now, these are the things that we'll be talking tomorrow. clinical aspects. We will not overload you.
Thank you, Doc.
Thank you, Doc.
Happy New
Welcome.
Year.
Thank you, Doc.
Happy New Year.
Happy New
Thank
Year.
you, Doc. Happy New Year.
Thank you, Doc.
Thank you po, Doc.
Welcome, welcome.
Thank you, Doc.
Thank you, Doc.
Happy New Year, Doc. Kaya pag pinabuto.
Wala. I still have 10 fingers.
Alright.
Okay.
Bye, Doc.
Bye-bye.